Wote. Jonathan is a Linux developer in Adelaide. He's been using Linux since 1990s, both privately and he's in his employment. He's contributed patches to the Linux kernel and other open source projects. So can we please welcome Jonathan?
Thank you. All right, so this talk is about the anatomy of a high-speed data acquisition system. So what I'm actually going to do is start just by giving a brief overview of the context of the system that I'm talking about, which is in atmospheric radar, just so that people can place the stuff that I'm talking about, and you know that there is actually a practical application for this stuff. I'm going to touch on the hardware side of the system as well, because the hardware forms a fairly significant portion of the system as a whole, and without knowing what the hardware is doing, the context of the software doesn't really make a lot of sense. I'm then going to progress on to the hardware, how that's structured, some of the decisions and trade-offs we had to make while we're doing this, and then follow down the data processing track to how we handle the ultimate data, and then summarise some conclusions and other things that we learnt along the way. So the context of this system is a data acquisition system for atmospheric radars, which our company ATRAD manufactures and sells. So these are radars that look up into the atmosphere, they transmit pulsed RF into the atmosphere, and they listen for reflections from the atmosphere. So the reflections that come down are extremely weak. We sell to meteorological organisations, research institutions like universities mostly, and the radars use various techniques for determining these atmospheric parameters. The most easily visualised thing is the Doppler system, which works in very much the same way that the Doppler effect does when you drive past sirens and things and they raise their frequency and drop their frequency as you go past them. The basic technique, as I said, is that we send a pulse up into the atmosphere and we listen for the reflections coming down, and we can tell the height that the reflection came from by how long the reflection took to come to us. So in high school physics, people learn about S equals VT and things like that, that equation. There's an extra factor of 2 in the radar equation because for us the time is, in terms of the height that it came from, the radar signal has travelled up and down before we get to see it. So to relate to the height of the radar, there's an extra factor of 2 in the equation. So the point there is that we can tell from the time that the radar reflection comes down to us where in the atmosphere that reflection corresponds to, and that can tell us about what the atmosphere is doing at that height. Now in terms of framing our data acquisition system, it turns out that we want to get data at a resolution of about 25 metres. Not every radar type needs it at that finer resolution, but there are some that do. So when we came to design this system, we said, okay, let's design for the most complex high-speed case, and then we know that we'll be covered for the rest of it as well. So that corresponds, you do the sums with our little radar equation there, and we need a sample once every 167 nanoseconds, which corresponds to a 6 megahertz sampling rate. Now, in order to determine what the atmosphere is doing, we need to deal with complex data. We need both the in-phase and the quadrature components of the data in order to determine phase and amplitude of the signal coming back, and that's how we can, in later processes, work out what the atmosphere is doing. So for each channel of receiver, we have 2 data streams, an in-phase and a quadrature, and each component is 16 bits. We're using 16-bit analog to digital converters in the system, notionally running as fast as 120 meg. You do the sums and you work out that the peak data rate per receiver channel is 24 megabytes per second. And the way that we analyse these data points coming back is that in order to maximise our signal-to-noise ratio, we have the option of combining the return from multiple pulses into a single data point by simple averaging. And that will come up later when it comes time to reduce this data rate somewhat. So we're dealing with quite a bit of, we're dealing with a fairly high speed thing already. It gets better. The hardware that we've decided to use is based on the Vertex 4 FPGA by Xilinx. The devices we're using is the FX12 device, which has an embedded PowerPC core in it. The original idea was actually to get that PowerPC core to do more, to do a little bit more of the data processing than what we wanted. But when we started doing some experiments and doing the sums, we worked out that the interface to the DDR RAM on the little daughter board that we were using wasn't fast enough. We weren't going to be able to get the data in and out across the bus fast enough. And so in the end, at least as far as the receiver goes, our system is essentially taking the data from the ADCs and piping it out pretty much straight away in hardware. I'll deal with that. I'll give more details about that in a sec. So the system actually has two components. There's what we call a digital exciter, which basically deals with all the transmission stuff that I'm not going to touch on much today. It forms the RF pulse. It keeps track of all the timing in the system and basically clocks the system along. The interesting thing is the receiver, which takes the reflected RF back, converts that to baseband, and then provides that baseband data stream as an output to the computer. So that's just a very, very simplified schematic of the system. On the left we have the antenna, goes into a low noise amplifier and a bandpass filter, mixed to a frequency synthesizer that converts it to our IF. That's then directly sampled by an ADC. We have our mixer, which splits it into the I and Q components. It goes through some more filtering, and then we have a multiplexer which takes those two components plus the similar components from other receiver channels and throws it out through a UDP engine that we've implemented in hardware. The digital receiver module, it turns out that for various reasons it's optimal to have receivers grouped in groups of 3. And so that multiplexer that I referred to before is multiplexing the I and Q channels from 3 receivers into a single data stream. And again, you do the sums, and you're now streaming your data out at 720 megabytes per second. We did all these sums and worked out that we needed to get that data into the computer somehow, and we went with gigabit Ethernet as that transport medium, and there are a number of reasons for doing that. The first was that it's well understood. We can use relative commodity-based hardware to transport those and to do aggregation. It's expandable if we need, in a different type of radar, if we've got lower data rates, we need more channels, we can just combine things in off-the-shelf switches and throw that into the computer. If we need more channels at higher rates, we can throw more Ethernet cards at the problem. So it seemed that the expansion paths there were relatively easy to do. The other advantage was that there wasn't anything at kernel level that we were going to need to do on the receiving PC. We can just utilise the existing Ethernet drivers that people who are much cleverer than I have already written to maximise bandwidth, and we get all the advantages of their work without actually having to effectively re-implement the wheel using something else to get that data into the computer. So, yeah, reason we chose Ethernet transport, the networking stack is already highly efficient, so we don't have to spend time reinventing the wheel trying to work out how to efficiently get data into the system. Alternative methods could involve using custom plug-in PCI cards, but again, we'd then have to write our own custom drivers for those PCI devices, which are doing essentially the same thing that the network drivers are. I've mentioned the expandability. We can add more NICs, we can add more switches into the system, and effectively we don't have any development work on that. Now for speed, so we're now getting into some of the other choices of the architecture. We went with UDP. I mentioned before that the initial idea was to stream this data through the PowerPC chip and maybe do some processing in the PowerPC chip to reduce the data rate, and then plug that out onto the network. Bandwidth requirements of the memory meant that that couldn't be done, And so we started looking at ways of getting that data straight off the ADCs straight into the Ethernet MACs, which are built onto these Vertex 4s. Doing that in hardware, which was the aim here, using TCP was not a feasible option. It's doable, but the resulting logic to do this with actual logic gates is incredibly complicated because of the checksumming requirements and various other details of the TCP packet. UDP is much simpler. You don't have to checksum the data. Details is much, much simpler because the headers are much simpler. So we ran with the UDP, and then we also fixed the UDP packet size. So somewhat arbitrarily we decided that we would send that's necessary. At the moment, the tests we've done, that doesn't appear to be needed. Things can keep up without any major problems. So we chose UDP. It is, of course, unreliable. Packets can go missing, and the protocol itself has no underlying framework that allows you to inherently multiply that by 4, went up by a factor of 4 and said, yep, that looks like that's working for us. So the data reception, I've touched on most of this, so I'll go through it fairly quickly. It has some soft real-time requirements insofar as it has to be able to, on average, keep up with the data that's coming in. But the instantaneous throughput doesn't have to match the incoming throughput, which reduces the requirements on this quite considerably. I've mentioned how it works with the popping of the data and putting it into the single pulse already, so I shall move on. The data handling, the processing, it's not as time critical as the other things. Obviously, it's still got to keep up on average, but again, because we're now getting further and further away from the real-time stuff, the requirements are a lot less. That's where we do the data reduction, the primary data reduction methods, which I mentioned before with the averaging. And the method of averaging the pulses, like I was saying, the term is coherent integration. There is a need to just be, as I mentioned, be a bit careful about how you structure the algorithms that do that averaging. But again, you don't want to over-optimise and spend too much time optimising this stuff for reasons that have been covered well in other talks at LCA this year and in previous years. Yes, once the data processing has been completed, we then push the total data out to the file buffer, and that concludes the high-speed section of that. The file buffer at the end will just accumulate the pulses, all the data points, until it's got as much as it needs, and then it'll dump that to the file at the last time. Once the raw data has been written to the disk, things become a lot less critical. That's where we start applying the more advanced to determine the atmospheric parameters that we want, like the winds and various other things. It can be time consuming. We're doing FFTs, deconvolutions on time series data that can last several minutes. But the key point is that the actual amount of data you're dealing with here is much reduced compared to the raw data flow. Because of the averaging and because of the fact we've averaged multiple pulses, the amount of data at this point is much reduced, and so you can afford to be doing FFTs and other things on the system. The advantage of the multi-core CPUs that we're now running means that that processing tends to live on a single core. The data acquisition side tends to live on 1 or 2 cores, and the two don't tend to interfere very much. We don't get a lot of core migration, relatively speaking. And so because they're sort of, because the whole thing is forming this continuous pipeline and there's no back references anywhere within that pipeline, the data just naturally passes from one to the other, and we don't end up getting stalls in pipelines and all the things that would otherwise kill the throughput. So the conclusions that we came away with is that when you've got control of the Ethernet network that you're using, or the network that you're using, you can make sure that you don't have silly devices on there that are going to wreck your throughputs and things like that. It's very, very good solution to the question of how do I get high-speed data into my computer. UDP, it's simple. It's, you can implement it in hardware like we have done, and as long as you've got the network controlled, you tend not to have drop packets and have to deal with the effects of losing data that way. Whilst TCP has many advantages, for real-time data, the UDP is probably the best. A, because you can do it in hardware and in FPGA, which is what we've done. But secondly, because we're dealing with real-time data anyway, if you've missed data, the data's gone. You've got no way of getting it back. And so as long as you can detect it, life moves on. In that respect, we're very, very similar to audio and video, in real-time audio and video stuff, in that once your data's gone, it's gone, and you've just got to deal with it. Very important to separate the data reception from the data processing, because it's the data reception that ensures that you actually get all the data that the device has sent you. The standard kernel.org kernel is now very suitable for tasks like this. As I said, we've found that we don't need to use the RT patch kernel anymore, and that's as much because the RT guys have pushed a lot of stuff into mainline now, which makes this stuff doable. So it's not that machines have got faster or the rest of the kernels got better. It's the fact that because of their efforts to push some of this stuff down into the kernels, we're now getting the latency effects in the standard kernel that we would never have got in years past. There's no harm in optimising the code as much as needed, but no more. Many people have said that, and it's a very important lesson to learn, because you can spend oodles of time optimising something or thinking that you're optimising something, and you end up finding that you've spent 2 weeks doing something, the code looks beautiful, and you run it, and it's given you maybe 0.1% increase, and it hasn't been worth it. Look for opportunities to use pipeline architecture in the data processing. So we were very careful in making sure that, you know, we did acquire, we did processing, and then we do you know, write to disk, and we pull that out and do the more detailed analysis after that. This allows you to make sure that the whole thing can parallelise without you having to do an awful lot of effort. There's not a lot of locking in any of this stuff, and that is a good thing for making sure that things down the fast path don't get stalled. And as I said there, finally, introduce the processing complexity as late as possible, because the further you can move that away from the real-time data acquisition and input side of things, the better things will be, because it means that that can just do its job properly. So there's some links and various other things. ATRAD is who I work for and who this work was done for. The SetR limits program is open source. You can grab it from that URL. For those who are interested in looking at it, the buffer pool and queue implementation is released. It's a dual license thing, GPL, plus we can still use it in our stuff. And then finally, the slides are up on the web and can be downloaded from that URL as well, and that's my email. So thank you very much.